All right, so last time we took our fit of the data, and that was the data is the blue curve, and the red curve is our fit, and then that's broken down into the two components, the two Gaussian peaks shown here in black and green. And the results for the fit are shown down here. So this is our amplitude, mean, and standard deviation for the second peak, right? So mean at 412. And then this is the amplitude, mean, and standard deviation for this first peak. You can see here the mean of 214. Okay, so what we want to do now is to use these values to go ahead and plot our curves using just our function, our Gaussian function g. Here, when we did our plots, we're actually plotting data that was generated inside of the fit. Okay, a different way of doing it, but this is really what we want to do. We have the values now for the fit, so we want to be able to just plot our function directly, and that will allow us to do things like add two data curves together, for example. All right, so we have our values, and we're going to go ahead and call those fit values Gaussian, right? And there's two sets in there. And then we're going to go ahead and we're going to call our P1 and our P2 values. So I'm just going to call our Gaussian function g, which was defined right here, which takes x, the amplitude, the mean, and the standard deviation, and returns this combination. Okay, so we're going to go ahead and take our function g, and if we insert the value for M1A, and let's see, values here, notice, is the fit vals Gaussian. I reassigned it to values so that every time we have a different function here, I don't have to go in and keep retyping new names. Okay, I can just change this piece. All right, so I'm going to put in the M1A, the M1 mu, and the M1 sigma right out of here. Remember, this is a dictionary, right? It's got the colon, so it's got a name, and then it has a value. So the way we would use a dictionary is we call the dictionary, and then we just simply give it the name, or the key is what this is. We give it the key name, and then it will go in here, find that key name, and take that value. So that's the notation that we use. So it's really nice actually to be able to use these as a dictionary. That's how it comes out by default. So we can go ahead and call the Gaussian a second time, but this time put in the values for our M2 fit, M2A, M2 mu, M2 sigma. And so that's our P1 and our P2. And then for our complete fit, all we do is add the two. Okay, so we're going to add the P1 and the P2 Gauss fits. All right, so that's all there is to it. We're just calling our function, sending it the values for our fit, and then we can add them together to see what our total fit looks like. So let's go ahead and do that. Notice by using the function itself, we're no longer tied to the x values that we pulled off of the original data. So we're going to go ahead and create a series of x values here, and we're going to actually create 150 of them. So I want to go from 0 to 900. That's my x-axis, and from 0 to 900 I want to create 150 points. So linspace is the way to do that. It's very nice. You give it the start number and the end number, and it will then, when you tell it how many points you want, determine what the delta x is between these so that it can have this start and this end. So we'll have 150 points. All right, so let's go ahead and plot now. So what we're going to do is we're going to plot our DSC data. So this is the data. Those are our points that we fit. We're going to go ahead and call our fit P1 Gaussian. That's our function here. Okay, and then our x values, which are here. We're going to go ahead and call our fit P2 values. And again, give it the x. And then we're going to call the fit, which we said was just the sum of the two. And I'm applying some coloring here and some labels so that we can go ahead and put in a legend. And so then there's our fit. So again, these two red curves are our P1 and P2 for our fit. We add those together and we get the blue curve. Okay, that's a pretty nice fit. So what we like to do is go ahead and compare this fit to the one from the paper. Right? Remember, we took the data for the authors P1 and P2. So if we can get an equation, a Gaussian fit for their P1 and P2, then we can do the similar thing and add them together to see what their overall fit looks like, because it wasn't given. So that's what we're going to do here. So this is the fitting routine now, except instead of fitting two Gaussians, we're just going to fit one Gaussian for P1 and one for P2, the author's data. So I'm going to still define two models in this case, but I'm no longer adding them together. I'm just going to run two fit routines here separately. So I'm going to go ahead and do my add parameters. I'm still going to define all the parameters for the first and the second peaks. Okay. And I'm going to pull off now my two sets of data. So my X and Y values for the P1 peak and for the P2. Remember, this was the experimental data that we took using the select data commands. So those are the two I'm going to fit separately. So my result for case 1 here, the P1 peak, I'm going to call model 1 this time, right? Just a single Gauss. And really all this is defining for me is this prefix M1. So it's going to grab these three values and ignore those. So that's my params. And my X values are from X1 here. And then my Y is Y1. So that gives me my fit. And then this term here, actually we don't need. I'm going to just delete it. There are no components. It's only one fit. Okay, we're going to do the same thing for the second one. We're going to fit now the Y2 data. I'm going to get rid of this piece. And that's it. So it's got my fits. They're in results. I did two separate fits. Okay, so each one with a separate Gaussian curve. So we're going to go ahead and plot now the data for X1, X2, data for peak 1, the data for peak 2. This is the author's data we pulled from the select data command that we actually fit. And then here now is going to give us our best fit results for 1, best fit results for 2. And so we'll go ahead and run that and see what that looks like. Okay, so those are good fits, good Gaussian fits, which we expect because they use the Gaussian, and that's what generated their two curves. So now we've got the values for the Gauss function, amplitude, mean, sigma for their peak 1 and their peak 2. All right, so we're going to go ahead and call these values author P1 and values author P2. Okay, same values. So now we can go ahead and plot those together just like we did before. Okay, I'm going to call them vals1 and vals2 now, just to make things a little easier. I'm going to call the Gauss function now and send in the values for my first fit. And then I'm going to call the Gauss again and send in my values for the second fit. So these are the two fits for the author's data. And then I can go ahead again and just add them, just like we did before, to get the overall fit. All right, so here's the data we're plotting. That's the points. I'm going to plot the P1 and P2 curves as red, and then I'm going to sum them and plot that as blue. Again, there's the sum, just a direct sum of those two. And so there is the author's P1, P2, and overall fit. If you go back up and look, I think ours does a bit better. They're missing a lot of points in here, and they tail off quite a bit and miss quite a few in here, and maybe a bit up here. Where if you look at our fit, right, we did a pretty good job up here. We fit all of these points, and we're still missing some of these, but we did at least catch these two just about. So we're definitely doing a much better job than what was in the paper. So now we've got the author's fit and our fit. So we're going to go ahead and call those two. So again, we're going to grab the data just so we can see our points. We're going to grab the author's fit and our fit, okay, from the previous two steps. So there's the author's fit, and then likewise above we had our fit. And so there they are together. And again, you can see our fit is doing a much better job in the dotted blue than the author's original fit. So, all right, so that's sort of step one. We could also, along with these, go ahead and include the P1, P2 values that we got and the authors got. So the author's P1 and P2, we just fit previously, generated these already. So they're red. And then if you go back, you'll see ours were called fit P1 Gauss, fit P2 Gauss, and those are shown in blue. So there's the overall data in black. Here's how it's separated out. So you can see that our peak 1 is much lower than theirs, and our peak 2 is higher and also shifted to the left. So there's quite a bit of difference for the deconvolution and how you interpret this data. And overall, though, remember, we did a much better fit. So far so good. What we're going to do in the next set is we'd like to take a look at a different way of fitting, because really when it comes to crystallization studies, Gaussians are not really an appropriate curve to deconvolute with. If it follows Avrami kinetics, we could use a peak derived directly from the Avrami kinetics, and that way we've got a physical model of what the peak shape should look like, and we'll do that and show that we can get an even better fit to this data, which means much better interpretation for what's going on with these two different structures that are crystallizing. Okay, I'm going to end there for now.